honor to be giving the first talk, and I've been in Santa Barbara for just about 12 hours, I think, and already like the rain. I will be talking about the latest population of merging compact binaries from the gravitational wave catalogs that we have. So let's go rewind back 10 years and look at this beautiful plot. I mean, this is really the plot that got me into the field. This is the strain time series measured in the Hanford detector. Yes, 4150914, the first ever detection of gravitational wave from a merging compact binary. Really, we can just stare at it and be happy about it and call it a day. But really, what is really important about that is to sort of take that time series and turn it into a measurement of parameters. In this case, the primary mass and the secondary mass of the two black holes that merge to form the gravitational wave signal that we saw. So this is great. It showed us that merging binary black holes, massive, about 30 solar mass each, exist in the universe, and that was the first ever detection of such a source. Right, but we are now in an era where we have grown our catalog 200-fold. I mean, we have roughly 200 events now, and this is a great plot. This is called, for people who have never seen this before, this is the so-called stellar graveyard plot. And each pair on this plot is a merging compact object, either a merger of two black holes, or a merger of two neutron stars, or a merger of a neutron star and a black hole. And so we have about 200 of these events now, and clearly we have now started to build up the population of merging compact binaries instead of just an elusive detection, which was the case about 10 years ago. Okay, so now it's fair to say that we have a largish catalog. And so really what the problem is to take a bunch of, say, primary mass and secondary mass measurements and build up what, for instance, something like the mass distribution of all merging black holes. This here is the primary mass distribution of merging black holes that have been detected by LIGO work of Kagra. I will, of course, talk more about this plot later in my talk, but the basic overview of what I'll be talking about today is how do you go from a bunch of measurements which are uncertain and have selection effects, for instance, to something like a measurement of population from these sources. Great. So, but why are we really interested about these things? The short answer is because population properties actually encode astrophysics. So, I imagine something like a version of this plot would probably be familiar to a lot of people in the audience. This is basically something like the ZAMS mass of a star on the horizontal axis versus the black hole mass that it produces when it undergoes, for instance, a supernova. And as you can see, there's roughly maybe a monotonic relation between the ZAMS mass and the black hole mass up to about, until you get to a ZAMS mass about 130 solar masses, after which the black hole mass goes to zero. We know this as, this is the theorized pair instability supernova mechanism that kicks in here, which basically there's electron-positron pairs produced, which leads to a drop in the photon pressure, and basically it just blows the star apart. But after some point, as you keep increasing the mass of a star, you should see a black hole mass. You should not have a black hole at the end of it. If you think of how this would imprint itself on the population of gravitational wave sources, you ideally should not see black holes above a certain mass scale, say about 70-ish solar masses. That's one. The other thing is, let's look at spins of black holes, especially something like spin directions of black holes. So we know that if, broadly speaking, if black holes were born together, live their lives together, die together, and merge as just two individual isolated objects, not in interaction with other objects in their vicinity or environment, we would expect naively that the spins of the black holes would be aligned due to orbital, with the orbital angular momentum direction, maybe due to tides, so on. And whereas if they were formed in dense environments through random encounters, say with other objects around them, we would expect their spins to not be aligned and would expect their spins to be random. So broadly, and of course there are caveats to this picture, but broadly you would expect that you have aligned spins in isolated formation and misaligned spins, isotropically misaligned spins in these dense environments. And essentially, if you now go into your catalog and ask what is the distribution of spin misalignments or spin alignments, that basically encodes the characteristic imprint of these formation channels. Okay, great. What else can you learn? Another question that you can ask is, are observed black holes actually made up of smaller black holes? In other words, did the black holes that we observe were formed by the merger of two black holes earlier on? So for instance, the default assumption we all make is that maybe there are two first-generation black holes, in a sense, black holes that were formed from stars that go around and merge together and form this 1G or first generation plus first generation event. But you could also have one of those black holes be formed hierarchically, as in from a previous merger of two black holes, which is something that you would call, say, a first generation plus second generation merger. And why are we interested in this? These, first of all, are a natural product of black hole assembly in these dense stellar clusters, but also they leave pretty interesting imprints on the data. So what's done here is they've taken these authors, Jarosa and Fishbach, take a fiducial 1G population. So the blue points here is some fiducial mass distribution and fiducial spin distribution of these 1G black holes. And essentially the histograms or the scatter plots in orange are the predictions for what the second generation black holes would look like. So first thing to note, of course, the second generation black holes extend to higher primary masses, for instance, as compared to the first generation black holes. And the other thing is just the fact that the spins are all concentrated about this magical number 0.7. This is not that magical a number. If you do a purely Newtonian calculation, just starting out with two non-spinning black holes and sort of try to evolve forward and ask what the final angular momentum or the final spin on the final black hole would be, you would get roughly a 0.7 answer as well. So this is not completely surprising, but really for most sane mass and spin distribution that you start off with, you always get this peak of at about 0.7 in the final spin of the black hole, which is why these second generation populations would always be spinning. Right. So all these things that I talked about are naturally imprinted on the population of sources. So if we try to search for this in the gravitational wave catalog, we can get some kind of information about these different formation channels. Okay, so now let's go to how do we actually measure the population. And I'll be talking about two ingredients here. So the first ingredient is that our black holes are actually have the detected set of sources actually have selection effects imprinted in them. This is a simple byproduct of the fact, at to zeroth order, that the gravitational wave amplitude from a system of merging binaries has this dependence on the mass and distance. Specifically, it goes as about the 5/6 power of this combination called the chirp mass and is inversely proportional to the distance. Which means that to zeroth order, it's inherently easier to detect massive binaries just because they have more gravitational wave power, and it's inherently easier to detect binaries that are close by just because they have more power when they reach the Earth. So our population is obscured by these selection effects, but because we know the signal from a merging binary to fractions of a percent from these general relativistic calculations and simulations, we can easily take our detected population and sort of correct for these selection effects and get the underlying intrinsic population of merging binaries, which is really what we are interested in, right? So there's a large effort within the collaboration to actually, within the LIGO-Virgo-Kagra collaboration to do this. One slight caveat is that we also need to account for search behavior, how gravitational wave searches behave, and if they are sort of tuned to detecting one kind of system versus the other kind of system. And so really the way to do this is to inject millions of compact binary coalescence, fake signals, into the data stream of the detectors, and then hand over those data streams to the gravitational wave searches, and then the searches process those fake data streams and tell you and give you a yes or no broadly a yes or no answer for whether the event is detected or not for every one of our fake injections. So this is an effort led by Reed, who kindly introduced me earlier, within the collaboration, and basically has a lot of people sort of involved in this whole effort. So let's step for a moment on the plot on the right. The blue histograms, or the blue points in this plot, are essentially the population of these gravitational or these fake signals that we injected, right? So they have some distribution. And the orange is the one that is the recovered population, so the ones that the searchers tell us is quote-unquote detected. So clearly you can see some very strong trends. For instance, if you look at the mass distributions that are injected and recovered are pretty different. This is, again, just a consequence of the fact that the gravitational wave amplitude goes as m to the 5 by 6. And then if you look at the distance histograms, you also see that there's a selection effect. The injected population had a large sort of support for a really, really large values of DL, but the ones that we recovered are systematically at lower distances, right? And so if you look at this in this two-dimensional plot of mass and distance, you see that this thing that separates these two histograms is roughly given by A proportional to m to the 5 by 6 by DL. There's also some really strong selection against the inclination, so the viewing angle of the binary, but not as strong selections against, say, the mass ratio or the effective spin. Great. So the other ingredient that we need to sort of get our information about the underlying population is a model for a population itself. What model do we choose for the population? In the community, there have been broadly two approaches. One is the so-called parametric or strongly modeled or strongly modeled approach, where we choose a form for the mass distribution. Say we say, okay, maybe we know that the mass function of stars is a power law, so maybe the mass function of black holes should be a power law, and then we just fit a power law to the data, and we get, say, the power law index and some maximum cutoff mass. Or you could say you think that for some reason there should be some pair instability pileup, and hence there should be some peak in the mass spectrum, so you add another peak in the mass spectrum, and so on. So basically you sort of construct a model from these principles that for some broadly intuitions about the physical processes that underlie the formation of these black holes, and you get some curve. But then you could take the completely opposite approach and say, okay, I don't know what the population is supposed to look like. I don't want to rely on my intuition, and so maybe I'll just model it as a superposition of really flexible functions. So this is this is one plot from Bruce Edelman's paper in 2022. So if you look at the red plot here, that's basically trying to fit a mixture of splines to the population. So, and we already see that it does sort of reproduce features which are not seen in this strongly parametric model. For instance, it does show, for instance, a strong peak at about 10 solar masses, which at least off the bat, you can't see in this power law plus peak model that was used in GWTC3. So yeah, so these are the broad ways of modeling the population. There are pros and cons to both of them. There's like a bias variance trade-off here. So if you take smaller parameters, you have a high risk for bias, but your variance is low. And of course, if you have these flexible models, which typically have a larger number of parameters, you might have lower bias, but you have high variance. Okay. Right, sorry. Okay, so now I'll just jump to the results that we found with the latest version of the gravitational wave transient catalog 4.0. That's the data set of mergers from the LIGO-Virgo-Kagra collaboration that was released back in August, end of August, basically. I should say this is a huge effort from a lot of people who are in the collaboration, some of whom are in this room, so I definitely want to acknowledge that. I had the extreme pleasure of leading the paper, leading the paper writing team, and putting various parts of the paper together. Okay, so let's dive in. The first thing that I want to show, and I will not talk about this much more in the rest of my talk, but this is the rate of binary neutron stars and binary black holes, and also neutron star black holes. I don't know why I forgot to highlight those. Estimated from the gravitational wave transient catalog 4.0. So basically, there's about 7 to 250 mergers per gigaparsec cube per year happening at redshift 0 of binary neutron stars. For binary black holes, that number is about 14 to 26, and for neutron star black holes, it's about 10 to 80. One thing to note is that this number is much smaller than, I mean, the median merger rate here is much smaller than what was estimated for, say, binary neutron stars when 170817 event was written up. And that's just because we have collected a lot more data, we have sensitive detectors, but we have not observed many more binary neutron star mergers, which is why the rate of binary neutron stars has been revised to lower. Okay, great. So let's start with the mass distribution of sources. So the best strong model that we find, or the parametric model that we find, is a broken power law structure, specifically 2 power laws that are modulated by these 2 peaks at about 10 solar masses and about 35 solar masses. This is clearly seen in the orange plot above. The blue plot is basically a non-parametric version. Again, you assume that the population is a mixture of splines, and you try to fit that to the data. And qualitatively, at least, both uncover the same features, although there might be some differences. Okay, so the first thing to notice is that there is a global peak of the binary black hole mass distribution at about 10 solar masses. And this peak, at least in all the model variations that we performed, was robust to choice of the model. So this peak likely exists in the data. There is a slight hint of some overdensity at about 20 solar masses. This is model dependent. So for instance, we tried a bunch of these strongly modeled or parametric models, and we really could not get overwhelming evidence in favor of that peak when we tried to add more complexity to our parametric models and try to find that peak. However, it is found robustly by this splines model. Yeah, so but whether or not it exists is still an open question, and more data will tell us if that feature is really real. There's this persisting feature at about 35 solar masses. This is either a peak of its own, or it's the break point of the power law, and the data does not have enough information to distinguish which is which. But it's for sure that there is some feature at that mass scale. And the other thing is, naively you would say, okay, maybe the parent stability supernova mechanism kicks in about 60 or 50 or 60 or 70 solar masses, but this mass distribution also shows us that there are binary black hole mergers that populate, at least in the primary mass, this region which is, say, greater than about 70 solar masses, which means that there is evidence in favor of a non-empty parent stability supernova mass type. Great. Of course, there are different explanations for each of these features. I think the jury is out on most of them. One explanation I specifically like for the peak at 10 solar masses is that they're formed through stable mass transfer, 2 stable mass transfer episodes, which naturally sets the mass scale and also the mass ratio distribution inside this feature. Okay, let's talk about the mass ratio distribution then. The default parametric model is to model this as a power law in the mass ratio. So the P of Q is proportional to Q to the beta. And the beta is constrained to be 1 plus or minus 1, essentially. If you again try to play the non-parametric game with splines here, you see that the model has some slight preference for putting the peak, putting a peak of the mass ratio distribution away from 1 at about 0.8 or so. which is also pretty interesting. One interesting thing that we did for the first time in this paper was trying to say, okay, now we have these different features that are coming up in the primary mass distribution, so specifically the 35 solar mass feature and the 10 solar mass feature. Let's try to give each of them a different power law index for their mass ratio distribution and try to measure them. These are the results of that analysis. Basically, peak 1 corresponds to the one at about 10 solar masses, and peak 2 corresponds to the feature at about 35 solar masses. And one thing that we find is that the black holes in the 35 solar mass peak actually preferentially merge with black holes of masses like itself. So they merge with black holes which are preferentially other 35 solar mass black holes when compared to the underlying continuum, and so the underlying power law continuum that we assume for our mass distribution. Similarly, we wanted to also understand, we and other people have also done this before, so especially Jackson Godfrey in a paper in 2023 had also looked for such a feature, but with updated data, we also see that the peak at 10 solar masses has a mass ratio distribution, so that's the blue traces, or here, has a mass ratio distribution that peaks away from 1 as well, specifically about 0.7. And I think the stable mass transfer episodes are a good candidate for this peak as well. Okay, so let's move on to spins. Specifically, I'll be talking about the effective in-spiral spin, which is essentially a mass-weighted combination of the spin projected along the angular momentum direction. So basically, these two angles that is defined on this plot, which is θ1 and θ2. So essentially, the chi effective would be m1 times the spin magnitude times cos θ1. Same thing for m2 divided by the total mass. So it's as I said, it's a mass-weighted combination of the spins. The reason why we're interested in this mostly is because this is the quantity that we measure best from the gravitational wave signal, because it defines the dynamics of a binary black hole merger. So just from the definition, one can note that the chi effective, or the effective spin, is 0 when the spins are 0, so the spin magnitudes are 0, chi1 and chi2 are 0, or when the spins are in plane, so cos theta is 0, theta is 90 degrees. So theta is just pointing in the plane of the binary. It's positive only when the spin axis is parallel to the orbital, and there's a component of the spin which is parallel to the orbital angular momentum, and it's negative only when there is some component of the spin which is anti-parallel to the orbital angular momentum. Just basically, all I'm trying to say is that if you vary the theta, you can get positive and negative spins. This is the distribution of the effective spins from gravitational wave transit catalog 4. So I want you to concentrate on the red curve here. So a few things that we can note already from this. So the peak seems to be about 0. So the peak of the chi effective distribution is about 0. But there is preference for both negative and positive spins in the data. Specifically, the distribution of spins seems to be skewed towards these larger values. So a simple way of looking at that is that this chi effective distribution extends up to 0.4 on the positive side, but does not extends only up to, say, minus 0.2 on the negative side. So it has more positive spins in the population than the negative spins, right? So okay, what do we understand from this? So let's talk about the negative side first, right? So I said that earlier that in isolated formation, you would typically think that these spins are aligned with the orbital angular momentum. And so any misalignment where you could get negative chi effective needs to be maybe from things that are dynamically formed in dense stellar clusters. So maybe this is some indication that there's already some population of data that are formed in dense clusters. Whereas for there's definitely presence for aligned component as well, specifically with high aligned spin. maybe there is also a population of things that are preferentially aligned to the orbital angular momentum in the data as compared to also the negative spins. Great. So I think this plot is really interesting and has a lot going on, and we can discuss more in the Q&A session. And aside to this, obviously, is that after we released the population of sources in O4b, or in O4b, which is the second half of the observing run, we did see systems, we did see one system with a confidently negative chi-effective. So this is GW241110. We also did see a system with a confidently positive chi-effective but misaligned spins, that is GW241011. Both of these have mass ratios about somewhere between 0.4 to 0.6, and these are good candidates for the hierarchical mergers in dense stellar clusters. Thanks, Reed. Okay, let's ask about what the redshift distribution of mergers looks like. Essentially asking the question, how many mergers happen per unit volume, per unit time, as a function of redshift? And with the latest catalog, we can say for sure that the rate of mergers per unit volume increases with redshift. So zero, like no evolution or a merger rate which is uniform in the co-moving volume and source frame time is actually ruled out. So basically, what I'm trying to say is something like this line here, which is horizontal, is essentially ruled out by the data. But the rate of mergers increases, and it's consistent with the evolution of the cosmic star formation rate density in the universe as well. I want to quickly also touch upon the original pair instability question. So I did show you that in the distribution of primary masses, there seem to be masses that sort of pollute this pair instability supernova mass gap. But if you look at it in the M1, M2 distribution, essentially, if you also ask what is the distribution of the secondary masses here, you see that there is some preference for a gap, or basically a sharp fall off in the rate in the secondary masses at about 45 to 55 solar masses. This is a plot from a paper led by Hui Tong, who's a graduate student at Monash in Australia, and a bunch of us in this room were also co-authors on it. So essentially, it seems like there are in the distribution of primary masses, there seem to be things that pollute the pair instability gap, but in the secondary masses, there seems to be a sharp drop-off. You could associate this with the pair instability supernova mass gap, and there have also been other authors who've found this with varying degrees of precision and uncertainty. Specifically, I want to point out two papers, one which is led by Fabio Antonini, and the other one which is read by Nadia Ray and Vicky Calogera, which came out a few weeks ago. Okay, so the last 2 minutes I want to spend talking about something that I am really excited about, and that is eccentric binary black holes. So eccentric binary black holes point to multi-body dynamics at play. And there might already be hints of eccentricity in the data. So this is a plot from a paper by Nihar Gupte et al. In 2024. And you see that at least in 3 events, there are some hints of eccentricity at about the 0.3 or 0.4 level at 10 hertz. This evidence is kind of, I mean, especially for one of these events, 200129, it is kind of dependent on how you deal with non-Gaussian artifacts in the data stream. But I'm really excited about how we can use, detection or even lack of detection in of eccentricity in our catalogs to try to constrain formation channels. So this is one example of it from a paper led by Mike Seven that was published in 2021. So this is like a study with mock data, but then on the x-axis is the number of observations. So the total size of a catalog essentially, and the beta c is something like the branching ratio for the cluster channels. And what Mike's plotting here is that as a function of the number of observations and the fact that you detect, say, 0, 1, 2, 3, or 10 eccentric events, how well can you constrain the fraction of the population that is dynamically formed? So this plot, I think, is really exciting because it says that at about 100 or 400-ish events, you can constrain the beta c to a few tens of percent, depending on how many eccentric mergers you detect. This is a difficult measurement to make. Waveform models with eccentricity are difficult to produce. Inference from then takes a long time. We also need to understand selection effects of these events better. So it's a challenging measurement, but I think it's one that's worthwhile. So I'll just summarize. Thinking beyond single event parameters and viewing events as a population can help us constrain astrophysics and hopefully yield insights on progenitor massive stars and evolution processes therein. I didn't talk much about the challenges, but there are huge challenges here. I mentioned briefly about how you model the population, strong versus weak models. There's also a question of how do you model correlations between different parameters. I think Salvo's talk later in the day will touch upon that. Selection effects. These injection campaigns, while it's doable, are also computationally expensive. So something that we need to look as to how to mitigate that cost. And the other thing is looking for robust features and how we actually have falsifiable features in our models, and hence we search for them in the data. But of course, the futures can help. The population of compact binaries will double by the end of 04, and I'm really excited about eccentric mergers. So with that, I'll stop. Then thanks for listening.
Thanks, Aditya. Just on time. If you have questions, remember you have to get up and walk to the microphone. No. Would you like to volunteer?
I will do it this time, but if other people do it.
Okay. Salvo, please, first.
Yeah, let me try to fix. Okay. Thanks, Aditya. Say again?
No, you can hear it.
Yeah, it should be on. Hello. I can be louder too. That's never a problem. Can you go back to the violin plot with the eccentricity?
Yeah.
So can you, well, do two questions. One, it's easier, which is like, what is the left-hand side violin? Is different waveforms?
I think it's just different priors, actually.
Okay, that was going to be my next question, which is, why a flat prior? I mean, if there is anything that my friends in the audience that do pop synth have told me, is that I should expect eccentricity to be small at the time of merger. So a flat prior is really overweighting large eccentricities, it seems to me.
Yeah, I agree with you, and you know, like that's right that these base factors are also dependent on the choice for prior. I think I can't remember in this paper what prior they chose for actually quoting those base factors, but basically, at least for these three events, it seems like the choice of prior does not matter much in the final estimation of the eccentricity. It could matter, for instance, when you try to do a hierarchical inference with these things, and you might have reweighing efficiency problems. But yeah, I mean, I think for any event that we confidently report as eccentric, we should probably try both priors and only report it as a confidently eccentric source if under both priors. It gives me a non-zero eccentricity.
Thank you. Sorry, this is like really
Okay, so you were suggesting that misaligned spins are evidence of dynamical formation. Have you taken black hole natal kicks into account in doing that?
No. So yeah, I mean, that's why I mentioned that like the simplistic picture that I painted has a lot of caveats. Okay. Black hole natal kicks is things that one thing that can sort of misalign the spins as well. Sorry? Yeah, but I mean, I'm talking about also the paper from Vishal Vaibhav and Vicky from back in the day, where they show that you could have significant misalignments as well.
Yeah, I mean, you can have small misalignments with natal kicks, reasonable, even with very high natal kicks. There is an underlying caveat about how the kicks work with the spin of the black hole, and I'm not going to go into this now. What you cannot get with binary evolution and natal kicks is anti-aligned. So the chi-effective negatives are definitely dynamical.
Okay, thanks. It was a good suggestion. In addition, thank you for volunteering to walk mics around. When you ask a question, please introduce yourself so that everyone online knows who's asking and people here who haven't met you before. Kaushik, please.
Hi, I'm Kaushik. I wanted to ask about some selection effects on the 10 solar mass peak. Could you go to the corner plot at the start of your presentation?
Yeah, this one?
Yeah, there. So, like, I don't see the numbers exactly for the like chirp masses, but so the injection there peaks at around 6 solar masses, like the left side, left hand top left plot. Yeah. So my question is like, if you just put a power law there, does what the detected get out still peak at like 30 solar masses? And then if that's the case, then like, is the 10 solar mass peak astrophysical or just observational selection effect?
Yeah, so first of all the plots that I showed you as results from the paper are all taking into account the fact that we have selection effects in the data and correcting for it. So I didn't go into the process of doing it, but then we put this all into a hierarchical Bayesian inference framework, which consistently accounts for selection effects. What's done here, and again, I didn't get to like the weeds of this plot, but basically we assume a fiducial injected population, and then we figure out, okay, what is detected based on that fiducial injected population. In this fiducial injected population, yes, the chirp mass distribution peaks at about 10 solar masses, right? But really, when we actually do the inference problem, right? So at the end, we actually reweigh these. So you can basically adjust the weights of the different numbers in, say, the injected distribution to get different realization of the detected distribution, and that's what we do in the inference process. So the 10 solar mass peak is real, and it's not just a consequence of what we've estimated the sensitivities to be, for instance.
Thank you.
Hi, thanks. Very nice talk. Can you go back to our slides about the spins of first generation and second generation black holes? Yeah, this plan. So I think I understand why the second generation around 0.7, but what do you assume about the spins of the first generation black holes?
So this is the spin distribution for the first generation black holes. So what was done in this review article was that the authors assume that the first generation distributions are basically, say, a realization from the population of things that were detected until then. This, I think, is about 4 to 5 years back. And so that forms the 1G distribution here. And then you take 2 draws from the 1G distribution and form a 2G black hole. And so, of course, your mass, of course, increases, and sort of the maximum mass is larger, and then you have spins which are concentrated about 0.7.
So these are from data?
This is data, so blue points are some realization from data with a realistic population, and then you take fits inspired by numerical relativity to sort of forward model, to model the orange points, essentially. And the inputs to those fits are basically 2 numbers drawn from this distribution.
All right, thank you.
Yeah.
Hi, thanks a lot for the talk. Tomer Shanar, Tel Aviv University. In the preceding workshop, we had a pretty interesting debate about whether the excess of negative spins is potentially a result of a very complex Bayesian machinery. A very complex Bayesian machinery, which is working on the data, and that the events which actually have well-confirmed spins are almost always positive. So I wanted to know your opinion about this.
I think, so it's true that like the negative chi-effective systems, it's slightly more difficult to measure them. And so also, if you try to ask how well can you measure the spins of negative chi-effective systems, that's also the individual spin posteriors are wider. So yeah, I mean, there is definitely one system which has a confidently negative chi-effective. I mean, I think there is enough, I mean, there might be still modeling challenges which are open. For instance, like the chi-effective distribution, we know should have correlations with maybe the mass ratio distribution, like for instance, the 2G, 1G mergers should be spinning and should have chi-effectives all over the place. So there might be other efforts in that direction, measuring correlations, modeling correlations, and so on, that might help in that case. But I think there is some fraction of the population that is negative chi-effective. The exact number might depend on the models, and at least in the models that we tried in this paper, we did find that a fraction of the mergers is definitely have negative spins.
Question?
Yeah. It was a very nice talk. I have 3 questions at least, but the major ones are how accurately can you measure the distances? Because it's a very complicated inversion, and the derivatives of A and A themselves go with the same power. The other is the eccentricity chi correlation. You touched on this, and there must be some sort of interesting science that can be derived by exploring that.
Yeah.
The third is, if there's eccentricity, you must get an estimate of the time since the injection of an eccentric orbit.
Yes.
Do you have some distributions of that, or can you extract any of that in this context?
So I'll answer your last question first. So,
Aditya, can you also repeat the questions, because I'm not sure they went in the
oh,
box.
okay. So the last question was about if you detect some eccentricity in the data, can you sort of rewind it and see when the eccentricity was actually injected into the system? The second from last question was whether there are eccentricity and spin correlations, if I understood it correctly. And the first one, I have conveniently forgotten. Sorry, the distance, yeah. How well can you measure the distance from the sources? Okay, let me just answer the question in the order you asked. So the distance is typically measured with tens of % of uncertainty on an individual event basis. So it's not a very well measured parameter. Of course, we would like to make it better because it has other...
The question is how you measure the distance.
How you measure the distance? So, okay, so especially from systems that are sufficiently in spiral dominated, so essentially low mass systems, you can get the chirp mass from the evolution of the signal. So as you said, the time derivative or something like that. So the amplitude only depends on something like chirp mass to the phi 6 divided by dl, and there are some terms that depend on the inclination angle, the viewing angle. So the chirp mass you get from the frequency evolution, and then all you're left with is this degeneracy between the inclination angle and the distance, and then essentially the fact that you can measure that one number and there's some degeneracy between them gives you a measurement of the distance. Is that a no? Okay.
Useful, thank you.
So, and the eccentricity spin correlations, were you asking about this from an intrinsic population level or okay, yeah, so yes, there should be that. There's one big challenge in that regard. I mean, typically if you want to measure these eccentricity spin correlations, you need waveform models which model both eccentricity and spin precession, for instance, especially if we think that these are formed in dynamical environments. We currently do not have very faithful waveform models in that region of the parameter space. We can model eccentric systems with aligned spins aligned to the orbital angular momentum pretty well, but the other ones, not yet. So there's a long way to go from just a theoretical waveform development side to go there. About the eccentricity distributions and how we can get constraints on where eccentricity was injected, I think people have not done this so far, and that's also because people have not, say, calculated what the eccentricity distribution of things from the data is. There are these 3 events that were found to be mildly eccentric, and again, like there are, as I said, there is questions about how you subtract non-Gaussian noise in the time of the event. And so this is 3 out of roughly 100. So we know that like the fraction of eccentric events has to be small. But there's nobody, I don't think there have been people who have done like the full problem and tried to measure the distribution of eccentricity and then, fold in formulas for how that would have looked in the past.
Thank you very much, and thank you for a wonderful talk.
Thank you.
Let's thank Aditya again.
Okay.